So, we are talking about robots. They assemble our cars, perform delicate surgeries, even explore other planets. These feats of engineering all rely on one fundamental concept: movement. But what gives robots the ability to move with such precision and flexibility? The answer lies in understanding degrees of freedom, or DOF. Just giving you a short overview of DOF. Here we have an industrial robot which showcases degrees of freedom in action. With 6 rotational joints, from the base to the wrist, each DOF enables specific movements. Together, they allow the robot to precisely reach any point in its workspace. This flexibility is key to performing complex tasks, from manufacturing to medicine, by positioning the end effector exactly where it's needed. Now let's dive into how robots move by understanding their structure. First, take a look at the human arm. Joints like the shoulder, elbow, and wrist enable movement, while the bones act as links connecting these joints. Now compare this with a robot manipulator from the picture on the right, where rigid links are connected by joints. Just like our arm bends and rotates, a robot's joints enable precise motion, mimicking human actions with remarkable accuracy. Now, on the left side of the picture is a revolute joint. Just like our elbows, it allows rotation around a single axis. Notice how the link connected to this joint can only move in a circle. And on the right, we have prismatic joint. Think of it like a slider. It allows linear motion along an axis, extending or retracting the connected link. Now let's examine 2 more. The universal U joint, shown in D, enables rotation around 2 perpendicular axes. Finally, the spherical S joint in E offers the most freedom, permitting rotation around all 3 axes, much like a ball and socket joint in the human body. These joints are crucial in determining a mechanism's degrees of freedom. So, what exactly are degrees of freedom? Simply put, it's the number of independent variables required to completely define the position and orientation of a mechanism in space. Think about how you would describe the position of your head right now. You'd need 3 values for its location in space, its x, y, and z coordinates. But that's not all. You'd also need to describe its orientation. Is it tilted up or down? Rotated left or right? We call these roll, pitch, and yaw. Just like your head, a robot needs 6 values to fully describe its end effector's position and orientation in space. This means that a rigid body in space has 6 degrees of freedom. The more DOF a robot has, the more complex and flexible its movements can be.
Here, the number of DOF is calculated using Grubler's formula, which states that for a mechanism having n links, considering the ground as a link, j number of joints, m be the number of DOF of a rigid body, m equals 3 for planar mechanism, and m equals 6 for a spatial mechanism, and f of I be the number of freedoms provided by joint I, and c of I, the number of constraints provided by joint I, where m equals f of I plus c of I. Now here, if we look at the table, we will understand how we got m equals 3 or 6 for different joints in a planar or spatial configuration. Mechanisms are broadly classified into 2 types, open chain and closed chain. Let's take a look at K-link planar serial chain for determining DOF. As it is planar, m will be 3. We can see there are 5 links considering the ground, 4 joints, and as there are 4 R or revolute joints. So, sum of Fi becomes 4. Using Grubler's formula, the degrees of freedom come out to be 4. An easier way to calculate this is by noting that the K-link chain, or also called KR robot, has n equals k plus 1 links and j equals k joints, with f of I equals 1 for revolute joints, simplifying the DOF to just k. So, the number of revolute joints equals the number of degrees of freedom. Now, for a planar 4-bar linkage with 4 links and 4 revolute joints in a closed loop, the degree of freedom for this structure becomes 1, meaning it's a rigid structure. Now, let's level up by comparing this open chain mechanism to the previous one. By adding a new revolute joint with an axis of rotation perpendicular to the existing joints, the planar system transforms into a spatial mechanism, making the mobility m equals 6. This new joint also adds a new link, giving us a total of 5 revolute joints, and applying the formula, we get 5 degrees of freedom for the structure. In the next example, notice how 3 links meet at a single point, forming what's called an overlapping joint. Recalling that a joint by definition connects exactly 2 links, the joint at this point of intersection should not be regarded as a single revolute joint. Rather, it is correctly interpreted as 2 revolute joints overlapping each other. The mechanism consists of 8 links, 8 revolute joints, and 1 prismatic joint, shown as a spring symbol. Applying the formula, the degree of freedom for this structure comes out to 3. Here we can see a Stuart Gough platform that consists of 2 platforms, the lower one stationary and regarded as ground, the upper one mobile, connected by 6 UPS legs which are divided into 6 lower legs and 6 upper legs. So the number of links becomes 14. And as there are 6 U joints, each with 2 degrees of freedom, 6 P joints, each with a single degree of freedom, and 6 S joints, each with 3 degrees of freedom, the number of joints becomes 18, thus getting a DOF of 6. In some versions of the Stuart Gough platform, if the 6 U joints are replaced by S joints, then DOF becomes 12, allowing 6 internal, torsional rotations about the leg axis. Now, this is interesting. As for our last examples, we have 2 similar structures, which may seem same at first. For the left structure, applying Grubler's formula gives an accurate DOF of 1. But when the same formula is applied to the right structure, it gives 0. When discussing the Grubler's formula, recall that we stated, this formula holds only if all joint constraints are independent. Let's talk about it a bit. In a robot, joint constraints limit certain movements. For example, a revolute joint restricts translation, but allows rotation. These constraints need to be independent, meaning each joint limits a different kind of motion. If 2 joints restrict the same movement, they overlap, and this can throw off calculations for degrees of freedom. Grubler's formula only works when these joint constraints don't interfere with each other, ensuring each movement restriction is unique. Since constraints are not independent here, any one of the 3 parallel links, with its 2 joints, has no effect on the motion of the mechanism, so we should remove 1 link, thus giving us the correct DOF of 1.